Hello, we are now going to do the Chapter 6 review worksheet, the Santa worksheet. And, I encourage you to, pause the video before each question and try to give it a shot and see if you can get it right. And correct me if I make any mistakes, which maybe I'll make a mistake. I don't know. But anyway, so let's look at this. This context 1 says the number of elves that call in sick each day at Santa's main workshop follows the discrete random variable below. And so here's the number of sick elf call-ins. And so it's always going to be either 0, 1, 2, 3, or 4. And 52% of the time it's 0, 21% of the time it's 1, and so forth. So these probabilities have to add up to 1. Something has to happen. So the way you find the probability of 4 is saying 1 minus the rest of these. Well, the rest of these add up to 0.89. So this has to be 0.11. So that would be the first thing. And so what's the probability that at least 2 call in sick? So the probability of at least 2, so that's greater than or equal to 2. So that's going to be either 2, 3, or 4. And so that is going to be 0.12 plus 0.04 plus 0.11. And so that would add up to 0.16 plus that would be 0.27 or 27%. So that is that. All right, so what's the probability that you're going to have less than 2 elves call in sick, given there's at most 3, given there's less than or equal to 3. That'd be at most 3. Remember, in this chapter, the probability of one thing given another is just the probability of the first thing, x is less than 2, over the probability of the second thing, the probability that x is less than or equal to 3, less than or equal to 3. So the probability of less than 2, well, that's going to be either 0 or 1, and so those add up to 0.73. Divided the probability of less than or equal to 3, well, that's all those. And so that's going to be that plus that plus that plus that, and that's 0.89. And so we would have 0.73 divided by 0.89, and that is equal to 0.82022 approximately. So there you go. And so that's how you do that. What are the mean and standard deviation? Now, to find the mean, and this formula is on your formula sheet, you can multiply every x times its probability, that times that, that times that, that times that, that times that, and that times that, and add them up. Okay, and it's not that hard to do. And then the standard deviation is, it has a little formula, and it's kind of tedious, but it's not that bad. But I'll just go ahead and show you how to do this with a calculator. And so what we'll do is we'll put these in list 1 and list 2. Okay, and so the way we do that is we hit the stat button, and then we hit edit. And so in list 1, we put over here, we put all the x values, the number of sick elf call-ins, 0, 1, 2, 3, 4, they go there. And then the probabilities will go in list 2, like that. And so then we'll do one variable stats. And so we will say stat, calculate one variable stats, and we put list 1. If it didn't say list 1 there, it's above the 1, and list 2 is above the 2. So if it didn't say that there, you do second 1, put list 1 there, and second 2 to put list 2 there. Then we do calculate. And there we go. So our mean is 1.01. So our mean is 1.01, and our standard deviation is 1.3379 approximately. And so that is that. Context 2. The weights of Santa's reindeer follow an approximately normal distribution with a mean of 700 and a standard deviation of 100. If you randomly select a reindeer, find the probability it weighs less than 650, probability that weighs less than 670. Well, that's going to be a normal CDF problem. And less than 670 is going to be negative infinity to 670. Our mean is 700. Our standard deviation is 100. So we label this, make sure and label it, LB for lower bound, UB for upper bound, mu and sigma. And so here we go. And so the way you do that, remember, the normal CDF is in the distribution menu right above the vars button. So you go second distribution, normal CDF. So negative infinity, that's negative infinity, but you just hit the minus, hit the negative sign, not the minus sign, hit the negative sign, and then you can just hit like negative 9 billion or something like that. Okay, the upper value is 670. The mean is 700, and the standard deviation is 100. So this is just a stock normal CDF problem. Really, we did this in chapter 2. And so that would be 0.38209, let's say. So that's that. So then we have this. What's the probability that it weighs less than 670, given that it weighs less than 710. Once again, in this chapter, the conditional is just the probability of that over that. So that'll be the probability that X is less than 670 divided by the probability that X is less than 710. Well, we just found that in number 4, so that's 0.38209. That's the numerator. The denominator is just do the same thing with 710. So if I just arrow up there and then just change this to 710, arrow over and make that 710. And so that would give me 0.539828, let's say. And so I'll just divide those two numbers. So if I just said 0.3820886 divided by the answer, and so that would give me 0.7078, let's say. Like that. And so that's how you do that. What is the 97th percentile? That's an inverse norm problem. It's the 97% of values are below this value. Of course, this is the same question is what value has 3% of the values above it? So this would be 0.97. Our mean is 700. Our standard deviation is 100. Like that. And so label this as left area, mu, and sigma. Because inverse norm is right below normal CDF. So we'll go second distribution, inverse norm right there. So inverse norm of 0.97. Our mean is 700. Our standard deviation is 100. So left area. And so that would be 888.079. So 888.079. And this is pounds. This has a unit. So it's pounds. So that would be the answer to number 6. Number 7, what is the IQR? Remember the IQR, the interquartile range, is Q3 minus Q1. It is the Q3 is the 75th percentile, Q1 is the 25th percentile. And so it is just inverse norm of 0.75 and inverse norm of 0.25. And so that's what I shall do. And so we'll do inverse norm of 0.75 with that meaning that standard deviation left area. And then we go like that. And so it is 767.45 approximately. And then we do the same thing with 0.25. So if I do second entry, it'll enter that last command, or you could just arrow up there, change this to 0.25 like that. And then I just subtract those two values, 767.44897 minus the answer. And that would be 134.898. 134.898 pounds. There you go. And so that's the answer to number 7. Number 8, one reindeer, Frank, has a z-score of 1.2. How much does Frank weigh? Remember, the z-score is equal to x minus mu over sigma. And so we'll just enter in these values. 1.2 is equal to x, which is Frank's weight, minus the mean, which is 700 over 100 standard deviation. So I just take 1.2, multiply it by 100, and add 700. So I go 1.2 times 100 is equal to, and then plus 700. So it's 820. And so that's Frank's weight. X is equal to 820 pounds. So he's a big reindeer. All right. So if you randomly select 3 of the reindeer, what is the probability the sum of their weight will be less than 2,000? Okay. So now let's think about 3 reindeer. Remember, 1 reindeer, all right, varies normally, mean of 700, standard deviation of 100. So 3 reindeer, okay, it will also vary normally. The mean, it's just going to be that times 3 is 2,100. But when you take 3 different ones, you can't multiply it by 3. It's a different thing than just saying, hey, multiply this by 3. That's a different problem. When you're getting 3 separate reindeer, you have to multiply the variance by 3. The variance of the reindeer is going to be 100 squared, which would be 1 and 4 zeros, so 10,000. And so the variance of 3 reindeer is going to be 3 times 10,000, and that's 30,000. 30,000, like that. So that's the variance. And you take the square root of that. That's the standard deviation of 3 reindeer. And so what's the probability that's going to be less than 2,000? We'll do normal CDF. And so here we go. So we shall do normal CDF So less than 2,000. So that would be negative infinity to 2,000. This is 2,100. And this would be the square root of 30,000. And so that would give me 0.2819 approximately, 0.2819. So there we go. All right, so then it says this, context 2 continued. The weights of Santa's bears follows an approximate normal distribution, mean of 800, standard deviation of 40. So the bears, approximate normal, mean of 800, standard deviation of 40. So they're in general a little bit bigger than the reindeer on average, okay? So if you randomly select one of Santa's reindeer and one of his bears, what's the probability that some of their weights will be more than 1650? So now with the sum of their weights, so reindeer plus bears. So reindeer plus bears, we're looking at the sum of their weights. It'll also vary normally. The mean, they add up to 1,500, so that's good. Now, we have to assume, we really need to be told, and I should have put that in the problem, that the weights of the bears and the reindeer are independent. And if that happens, then we can add the variances. You cannot add the standard deviations. It's like the Pythagorean theorem. You've got to square these values, add them, and take the square root. So the variance of the bears is 40 squared, which is 1,600. So the variance of the reindeer plus the bears is going to be 10,000 plus 1,600. And so that's 11,600. And so the standard deviation would be the square root of 11,600. Whenever you add together random variables, you don't add their standard deviations. If they're independent, you square them, you add them, and take the square root, just like the Pythagorean theorem. Now we can do normal CDF. So I'll write this out one more time. Normal CDF from 1650 to infinity. Our mean is 1,500. Our standard deviation would be the square root of 11,600. Of course, you would label this to get full credit. Label this as lower bound, upper bound, mu, and sigma. And so let's see what we get. And so we shall say normal CDF from 1650 to infinity. Our mean is 1,500. Standard deviation would be the square root of 11,600. It's like that. And so that would be equal to 0.08185. Thus, that is the answer. That is the answer to number 10 right there. All right, so if you randomly select one of Santa's reindeer and one of his bears, what's the probability the bear weighs more than the reindeer? All right, now in general, the bears do weigh more than the reindeer on average, but it could, by chance, you get a light bear and you get a heavy reindeer because they both vary. All right, maybe you end up with a reindeer heavier than a bear. All right, so whenever you're asked to compare two distributions, which one is probably this is more than that, or this is less than that, subtract them. So we'll subtract them. It says bear weighs more than reindeer. So we'll say bear minus reindeer. It will also vary normally. When you subtract two normal curves, you get a normal curve. You subtract the means. So bear minus reindeer would be 800 minus 700, which is 100. But you do not subtract the standard deviations or variances. You add them just like you did when you added. So this would still be the square root 11,600. So that's that. And then you say to yourself this, well, if the bear weighs more than the reindeer, if B is bigger than R, then B minus R is positive. So we're going to do normal CDF with the positive numbers. The positive numbers are 0 to infinity. So it'd be 0 to infinity. Mean is 100. Standard deviation, the square root of 11,600. To get full credit, label this as lower bound, upper bound, mu, and sigma. Let's see what we get. And so that's going to be normal CDF from 0 to infinity. Our mean is 100. Our standard deviation is still that. And so we would get 0.8234 approximately, 0.82342. So it happens more than half the time, and you'd expect that because the bears in general weigh more than the reindeer on average. But so it happens about 82% of the time. So that's that. On to page 2. So let's see what page 2 has for us. And so it says, a certain group of Santa's elves are a bit disgruntled. They have formed a gang. How about that? So 28% of the toys created by this elf gang are defective. if you randomly select toys from this gang, find the probability the first defective toy you encounter is the fifth one. Now, you need to recognize this as a geometric problem because it's concerned with when is your first success here. Now, success isn't necessarily a good thing in context. And a matter of fact, here's a bad thing. It's a defective toy. But we'll keep this. So the probability of success is 0.28. That means the probability of failure, 1 minus the probability of success, 1 minus that's 0.72. So this is saying the first effect was probably the first effective toy is the fifth one. That means the first 4 had to be failures. So the probability of this is going to be 0.72 to the fourth. That'd be 4 failures. And then the fifth one is a success. And so it's times 0.28. And so the way you do that is we will enter in 0.72 and then the up arrow button right there, that's going to raise it up there to the fourth power, hit enter, and then go times 0.28. And so that gives us 0.07525, 0.07525. That's how you do that. So what's the probability the first defective toy is on or after the fourth one? Well, if it's on or after the fourth one, we know the first 3 had to be failures. Okay, so we know 0.72 to the third power. We know the first 3 were failures. We don't know when our success was. It could have been the 4th, the 5th, the 6th, the 7th, and so forth. Oh, we don't know when it was. So the probability on or after the 4th is just 3 failures. It's just that. We don't know when our success was. So we'll go 0.72 to the power 3. And so that is 0.3732 approximately. 3732. That's all there's to that. What is the mean of when you would encounter defective toy for the first time? The geometric mean is 1 over p. It is 1 over 0.28. And so let's see what that is. So 1 divided by 0.28. So that is 3.751, 3.571 rather. So that is that. So that is the mean of a geometric situation. Then it says this: if you randomly select 7 of the gang's toys, what's the probability that exactly 3 will be defective? That you have to recognize as a binomial situation. We have a fixed probability of 0.28. We have a fixed number of trials at 7, and we're asked about a number of successes in a success failure situation. So it's definitely a binomial situation. So we'll do binomial PDF, PDF for 1 point. So it's going to be binomial PDF, where our n is equal to 7. That's our number of trials. Our p is equal to 0.28. And then our x is equal to 3. And you list those in that order with these letters to get full credit. If you left out the letters, you wouldn't get full credit. All right, so binomial PDF is in the distribution menu, right? Is below normal CDF. So we go second distribution, we scroll down to binomial PDF. PDF is for 1 point and CDF is cumulative. So we want PDF here. So PDF, our number of trials is 7, our probability of success is 0.28, and our number of successes is 3. And so that would equal to 0.20648 approximately. Now, there's a formula in your formula sheet you need to be aware of, all right, and you need to be able to use that does a binomial PDF for it, that is binomial PDF without your calculator. And it would be this: it would be 7 choose 3, which is basically defined as 7 factorial over 3 factorial and 4 factorial. And so then we have 3 successes, so that'd be 0.28 to the third power times, and that means we have 4 failures, which is 0.72 to the fourth. Okay, and if you multiplied all that out, you would get that. But anyway, but you can use binomial PDF, but you have to be able to recognize that in a potential multiple choice problem. So if you randomly select 7 of the toys, what's the probability that at most 3 will be defective? Now let's think about this. If you have 7 trials, what are all your possible number of successes? Well, you could have 0 through 7 successes. You could have 0 through 7 successes. So you could have 0 successes, 1, 2, 3, 4, 5, 6, or 7 successes. Those are all the possibilities if you have 7 trials. We want the probability of at most 3. At most 3 would be 0, 1, 2, or 3. Okay, and so we will add, so we want to add up all these probabilities. Now we could do exactly what we did in 15 and do it 1, 2, 3, 4 times, okay, and add all those up. But we're going to use what is known as binomial CDF. So it's going to be binomial CDF. CDF means cumulative. It means not just that value, but every value of that and below it. And so we're going to enter in n is equal to 7, RP is equal to 0.28, and our X is equal to 3. And so when we do that, now CDF is right below PDF. So we will go second distribution and go to Binomial Cdf right there for cumulative. Our X is 7, our P is equal to 0.28, and our number of successes is 3 or below. CDF means that or below. And so we would get that would be 0.8984 approximately. Yeah. So there we go. If you were to randomly select 7 of the toys, what's the probability that at least 3 will be defective? So a probability of at least 3 successes. In other words, 3, 4, 5, 6, or 7. So once again, our possible number of successes, 0, 1, 2, 3, 4, 5, 6, or 7. We want the probability of at least 3. So that would be that. We do not have a calculator function that tells us the probability of a certain value or above it. But like in number 16, we do have a calculator function that tells us the probability of a certain value below it. And the thing about it is, when you look at this, you realize all the probabilities of all these numbers have to add up to 1. So if you wanted to find the probability of 3 or above, you could just say 1 minus the probability of 2 or below, and we can use Binomial Cdf to find that. So the probability of greater than or equal to 3 successes is just 1 minus the probability of that not happening, which would be less than or equal to 2 successes. And we can use Binomial Cdf to find that. So that's 1 minus Binomial Cdf, where once again, our n is equal to 7, our p is equal to 0.28, and our x is less than or equal to 2. And let's see what happens when we do that. So we'll do Binomial Cdf, where our n is equal to 7.28, and now this is 2. And so this would be 1 minus 0.6919. And so that, in fact, so we'll say 1 minus that value. And so that would be 0.3081 approximately. So thus that is the answer to 17. If you were to randomly select 7 of the toys, what are the mean and standard deviation? Well, this is on your formula sheet. So the mean is just equal to n times p. And so that's equal to 7 times 0.28. And so let's see what that is. And so 7 times 0.28. And so that is equal to 1.96. And then also on your formula sheet, the formula for the standard deviation of a geometric random variable, and that's going to be n times p times 1 minus p. And so that would be equal to the square root of 7 times 0.28 times 0.72. And so let's see what that is. And so this would be the square root of 7 times 0.28 times 0.72. And so it's 1.1879, 1.1879. So there you go. That's how you find the mean and standard deviation of a binomial random variable. Now, okay, here we go. Let's look at this one here, a bit of a specialty problem. So this one says this: Santa is marketing a new game that he hopes will raise money to build a mansion at the North Pole. In the game, you're dealt a card from a 52-card deck. If it's a face card, a jack, queen, or a king, you win $50. If it's a numbered card 2 through 10, you win $20. And if it's an ace, you win $300. How much would Santa have to charge per play to break even in the long run if this is the amount he's giving out for the game? Well, let's see how much he's paying out on average. And so the way you find that is recognize this is a discrete random variable. That is, let's think about the money that's being made. He's either giving out $50, $20, or $300. What's the probability? So he's either giving out $50, $20, or $300. What's the probability that he's going to give out $50? Well, he gives out $50 if it's jack, queen, or king. Okay, so that's going to be, there's 3 possibilities there out of the 13 possible types of cards. Or you could reason it, there's in a standard deck of 52 cards, there's 4 jacks, 4 queens, and 4 kings. So that would be probabilities 12 out of 52, which simplifies down to 3/13. What's the probability he's going to give out $20? Well, that's the number of cards 2 through 10, and there's 9 of those. So that would be 9 out of 13. And then what's the probability he's going to have to give out $300? That's all the aces. There's 4 aces, 4 out of 52, which is 1 chance out of 13. So how do we find the average amount he's given out? And that's just like what we did, right, on this other thing right there. When we found the mean of these things, multiply them and add them up. And so to find the mean of a discrete random variable, of course, I could put this in list 1 and list 2 in the calculator and do one variable stats, but I'll just multiply these. And I'll say, well, that times that, that's going to be 150 out of 13, and then 20 times that, that'll be 180 out of 13, and then 300 times that, that's going to be 300 out of 13, and you add all these up, and you got yourself the mean. All right, and so let's do that. So this would be 150 over 13. So I'll go 150 divided by 13 is equal to, and then plus, and then 180 over 13 plus parentheses 180 divided by 13, close parentheses, and then plus the last one, which would be 300 divided by 13. And so this would be 300 divided by 13. And so that's 48.4615. So $48.4615. So that is the average amount he's giving out per play whenever anybody plays this game. So that is the amount he would have to charge per play to break even. So that's how you do that. Then it says this: if Santa charges $70 to play the game, okay, how many plays would you expect it for Santa to take for Santa to pay for his $500 million mansion? $500 million mansion. He's building one heck of a mansion. So anyway, so if he's charging $70 per play, well, his profit is going to be, his profit per play is going to be 70 minus 48.4615. And so let's see what that is. So I will just say 70 minus the answer. And so that gives me 21.5385. So 21.5385. That is his profit. So how many times is he going to make that to make 500 million? So we will divide 500 million. 1, 2, 3, 1, 2, 3 divided by 21.5385. And so I will say 500 million, 500, and then 1, 2, 3, 1, 2, 3 divided by the answer. I think I put enough zeros there. Okay, and so we would get that number. So we would get 23214,285.71. So let me see, 23214285. So that would be like 23 million times. Okay, so that's how many times that he would have to have someone play the game for him to pay for his $500 million mansion. Number 21, the amount of time that Mrs. Claus spends bobsledding each week follows a uniform distribution that goes from 2 to 11 hours. All right, if you randomly select a week, what's the probability she spends less than 5 hours bobsledding? So the key word there is uniform. So I'll draw my little rectangle down here. My little rectangle, my uniform distribution is going from 2 to 11. If I randomly select a point in this rectangle, probably less than 5. So 5 somewhere down here. There's 5. There's less than 5. And so from the area of this shaded region from 2 to 5 is 3. So it would be 3. So this is going to be 3 over the total area of this thing from 2 to 11 is 9. So the area of the total rectangle is 9. So it's 3 9ths or 0.3 repeating. So that's how you do the uniform problem. And so what's the probability, one thing given another, what is probability she spends less than 5 hours bobsledding, given that she spends less than 9? Of course, once again in this chapter, that's going to be the probability of less than 5 divided by the probability of less than 9. Well, we just found the probability of less than 5, so it's 3 9ths. What's the probability of less than 9? Well, 9 is somewhere up here. Okay, so now our shaded region is that. And so to go from 2 to 9, that would be 7. So that would be 7. And then the whole thing would be 9. And so that simplifies down to 3 7ths. And that is it. That is your review of chapter 6. Send me any questions you have about that, and I encourage you to to study your book and your note sheets, and please ask me any questions that you have about chapter 6. Thanks for watching the video, and I hope you have a super day.